Planes. So by plane, I mean a flat surface. So picture this book. How do we define a plane? Well, if we were talking about lines, like we were before, a line is defined by a slope and a point. So a lot of different lines can have the same slope, but if I say slope and a point, that locks the line in. If I say just a point, then you can have an infinite number of lines by bringing the slope. All right, planes. If I pick a point, there's like two slopes, right? I can tilt this way and still be at this point, and I can tilt this way and still be at that point. So what we're saying then defines a plane is the point, a point on the plane, we'll say a point that the plane goes through, and so I can sort of specify all these different ways a plane can tilt. I'm going to say a point and a vector. And the vector I'm going to be talking about is the normal vector, the vector perpendicular to the plane. So here's the plane, and here's the normal vector. So once I specify this normal vector, perpendicular to the plane, now I can't tilt this plane anywhere. So now normal vector locks down the tilt of it, and then the point locks down sort of the elevation of the plane, let's say. So a plane then is defined by its normal vector, which we normally call n, and a point on that plane, again, r0. Now, here's this plane. We want to get an equation for every point on this plane. Well, if I think about r0, that's the point that's on the plane. r0 is our one point that we know is on the plane. And let's say that that point is right here in the center of my plane. It's a book. But anyway, any point that's on this plane then, the vector from my point that I know, from r0 to any point that's on the plane, gives me a vector that lies in the plane. Doesn't matter where I put that x, y, z point on the plane, the vector that goes from r0 to the point on the plane lies in the plane. And it's always perpendicular. This vector is always perpendicular to my normal vector. So I'm going to get a pencil. Here's starting off at r0, going to any point, every general x, y, z point on the plane is perpendicular to that normal vector. That means the dot product is 0, and that's what we're going to use. So every point on this vector, r minus r0. So this r, that r is our x, y, z point, our general point on the plane, all points on the plane. It's orthogonal to the normal vector. So let's call this normal vector ABC, and we're going to make the scalar equation of that plane. So I'm taking the normal vector ABC. Well, let's write it like this first. Taking the normal vector ABC, and I want to dot product that normal vector with the vector that's r minus r0. And this r vector then, that's the vector that just general x, y, z. So that's all points on the plane, all representative points on the plane. And then this r0 vector, that's some number x, some number y, some number z. Those are numbers. So that's going to equal to, there's our normal vector. I'm dot producting against this piece here. And it's perpendicular, so that dot product is equal to 0. Now let's distribute, and we know we can distribute dot products. We saw that before in another video. If I distribute across this minus sign, I'm getting minus this ABC dot product, this R0, this point on the plane. and that equals 0. Now, what I'm going to do, because I want the scalar equation of a plane, that's of a certain, scalar means no vectors in my equation of the plane. So I want this to be, I want this to be no vectors. So I want this to, I want to get rid of all these vectors. Let's move this, since this is minus, A, B, and C are a number, given by the, whatever the normal vector to the plane is. Lost my Tintin book here. So wherever the normal vector to the plane, this is a number, an A, a B, a C number. And R naught is a number. So if I dot product ABC with some number R, this is just a number. Let's call it D. So I'm calling the normal vector dot product with this R naught vector, I'm calling it the number D. So now I get, if I bring that over to the other side, I get this equals the number D. That highlighted is what I'll call D. And now let's actually do our dot product. That's going to be first times first, plus second times second, plus third times third. And here is the equation we want. That's the scalar equation of a plane. There's 4 parameters, A, B, C, D. Oh, and no vectors anymore. What? Oh, it's written funny here. Let's write that as C times Z. That's better. Okay, there's 4 parameters, A, B, C, and D. What do they mean? Well, A, B, and C, that's the normal vector. What's D? D is the number that gives me the height. It's a measure of the height of the actual plane. How do I figure out what D is? Well, once I know what A and B and C are, I can just plug in any point that's on the plane and I can solve for D. But at least we've made what we're referring to then. If we say scalar equation of the plane, that's what we mean. There's 4 parameters. 3 of them, the A and the B and the C, are from the normal vector. The D has to do with the height, because many different planes can be all parallel. They can all have the same normal vector, but only one of them goes through the point R naught. Only one of them has that specific D value. All right. We made our scalar equation of the plane. So now let's answer a question. Find the equation of the plane that is parallel to both vectors and goes through the origin. Oh. Now, there's 2 ways to answer this question. Because it just says equation of the plane, they're not telling me vector equation of the plane or scalar equation of the plane. So let's first find the vector equation of the plane. Now, vector equation of a line, that was, what do we need for a vector equation of a line? I needed a point and I needed a direction vector. Well, a plane has 2 direction vectors, let's say. So for a plane, I need 2 vectors that both lie in the plane. One that lies in the plane like this, and some other one that lies in the plane. 2 vectors that lie in the plane that are not parallel. And so the vector equation of a plane is going to look like the 3D extension of the line. So that x, y, z, that's every point on the plane. It's going to be equal to a point on the plane, which we were calling, if I use the same idea, if I use the same notation from up there, that's R naught plus. Now a plane is a 2-dimensional object. A line is a 1-dimensional object. A plane is a 2-dimensional object. So I need 2 parameters. So I'm going to say k. So it's k times the first vector plus t times the second vector. Now if I pick a t and I pick a k number, oh, what's r naught? It goes through the origin. So r naught is a point on the plane. So our r naught is 0, 0, 0. Let's write it in there for completeness. So now there, I'm done. That's the vector equation of my plane. Notice if I were to get rid of this, that would look like a vector equation of a line, but it's two-dimensional. It's a plane. Pick a t value, pick a k value, plug that in, and you'll get a point on the plane. Every different k-t pair that you pick gives you a different point on the plane. It's two-dimensional. So there's the vector equation of the plane. That's not what we built up here, though. Let's get the scalar equation of that plane. So now I want scalar of the same plane. So what do I need? I need to know the normal vector. So I need to get the normal vector, and the normal vector is perpendicular to the plane. These two vectors are parallel to the plane, so I need a vector that's perpendicular to both this vector and this vector. Oh, how do I get a vector that's perpendicular to those two vectors? That's going to be the normal vector. You know where I'm going with this. I'm going to take these two vectors and cross product them. That'll give me a vector that's perpendicular to both vectors. That'll be the normal vector. That's what I want. So let's do our cross product formula. So that's going to be -1, 0. Now the middle one is always negative, so I got to be careful here. So that's going to be -1, -3, that's -4, minus a -4 is a 4. Now I'm going to check my algebra afterwards. So let's see here, we got a 0 and a -1. So if I'm correct, this vector is perpendicular to both vectors. Let's dot product it against 1, 0, -1 to see. That's going to be 1 times -1, it's -1. Plus 0 plus 1. It is at least perpendicular to this second vector. Let's check the first. 1 times -1 is -1. -1 plus 4, -3. Yep, so we did our cross product correctly. Or at the very least, now I have a vector that's perpendicular to both of these vectors that are parallel to the plane. So this must be the normal vector to the plane. How does that help me? There's my A and my B and my C. So A is -1, B is 4, and C is -1. So the equation of the plane is now -x plus 4y minus z is equal to d. The only parameter I don't know now is d. All I need to do is plug a point, any point, on the plane to figure out what d is. It goes through the origin, it goes through the point 0, 0, 0. So when I make x equal to 0 and y equal to 0 and z equal to 0, I get d is equal to 0. So my plane then is -x plus 4 minus z is equal to 0. That's the scalar equation of a plane. Now, I can stop here. That's the right answer. Probably if I turn to the back of the book, they'll have written it like this because there's like one less minus sign. They'll just multiply this whole thing through by -1. That's fine. If what they were thinking then is, if this is the normal vector to the plane, then this is the normal vector to the plane, right? If I just multiply that normal vector by -1, it flips it backwards. It's still perpendicular to that plane. So now we found the scalar equation of that plane. Here's another, find the equation of the plane. Let's find them both then. Find the equation of the plane that contains the 3 points. Now for the vector equation of the plane, I needed two vectors. I have 3 points. So for the vector equation of the plane, I needed a point. Now I've got 3 points. I can pick any one of these points. I'm going to pick the 0, 0, 2. Arbitrarily, I'm picking the point. Now I need I need two vectors that are parallel, that lie in the plane. Well, I've got 3 points here. So let's think about it like this. There's the point 1, 1, 1. That's in the plane. There's the point 2, 3, 4. That's in the plane. There's the point 0, 0, 2. That's in the plane. I need two vectors. Well, here's a vector. Moves from 0, 0, 2 to 2, 3, 4. That must be the vector. The x goes up by 2, the y goes up by 3, the z goes up by 2. That's the vector 2, 3, 2. Here's another vector. The x goes up by 1, the y goes up by 1, the z goes down by -1. There's two vectors. I could use those vectors. The vectors 2, 3, 2 and 1, 1, -1. So 2, 3, 2 and 1, 1, -1. Boom. There's my vector equation of the plane. All I needed was a point and the two vectors. If I want the scalar equation of the plane, it's going to be the same idea. So scalar equation of the plane. I need the normal vector and I need a point that's on the plane. So let's get our scalar equation of the plane. And I'm going to get it in the same fashion. Okay, I need to get the normal vector, so I'm going to cross product those two vectors because I need the vector that's perpendicular to both of them. So let's cross product them. That's going to be -2, -2 minus 2 is -4. The middle one is minus. That's going to be -2 minus a -2. That's going to be 0. And the last one is going to be 2 minus 3 is -1. Okay, now I'm doing arithmetic in my head. I got to make sure that this is, I don't like this. I made a mistake. How do I know? Well, it's not perpendicular to this first one. So I must have made an error. I got to go back and check. But that's the thing about getting a normal vector using the cross product. Yeah, there's a lot of arithmetic, and I obviously mess it up. We can check though, because it's not perpendicular. The dot product of this vector against this vector is not 0. So let's do our cross product. Let's do our cross product again and make sure we get a perpendicular vector. So I'm expecting you guys to check as well. So now I've taken the cross product and I've checked that my answer is perpendicular to both of these. The dot product of my answer with this vector is 0 and with this vector is 0. So that is the normal vector. So remember, we're looking for scalar equation of a plane. So that's my A and my B and my C. So the plane is -5x plus 4y minus z is equal to d. Now I just need to figure out what the value of d is. I pick any point that's on the plane and sub it in for the x, y, z to figure out what D is. I had 3 points. Any one of those points will give me the same D value. So I'm going to choose this one because it's just easier to plug in. Because I'm plugging in 0, 0, 2. That means D must be equal to minus 2. This is the scalar equation of the plane that contained those 3 points. Now, am I right? Well, if all 3 points are on that plane, then I'm right. So if I make x equal to 1 and y equal to 1 and z equal to 1, that's going to be minus 5 plus 4 minus 1 is minus 2. Okay, so the first point is on the plane. If you check these other 2 points, they will also be on the plane. So if you get one of these, find the scalar equation of a plane that contains the points, the 3 points. Whatever you get at the end, you can check to make sure it's the right answer by plugging all of those 3 points in and seeing they satisfy the equation. All right, what else can we do? What else have we done? We know how to get the scalar and the vector equation of a plane. That's what we've done so far. Oh, this next question is asking me find the angle between 2 planes. And they've given me 2 scalar equations of the plane. How do I find the angle between them? Well, what do I mean by angle between them? Again with the books. But here's 2 planes. I want to know what that angle is. Well, here's the thing. Besides it being difficult for me to hold. If I want to know the angle between these 2 planes, if I have the 2 normal vectors, okay, I don't have enough hands, but the normal vectors intersect at the same angle that the planes intersect at. That's what I'm trying to tell. So if I could figure out the angle between those 2 normal vectors, then I would have the angles between the 2 planes. Oh, one normal vector, and let's just call that, I guess, normal 1. I know what that's equal to. From this first, I can just read it off. It's 1, 2, 3. Well, that's unimaginative. The second normal vector from the other plane is equal to 2 minus 3, 0, because it's like 0z. So now I just need to know what's the angle between these 2 vectors. Oh, that's a dot producty thing. So all I got to do is find the angle between these 2 vectors using dot product. So here's the formula that we're going to be thinking about. It's going to be when I take these two vectors and dot product them together, I'm going to get the magnitude of one the magnitude of the other, and it goes to the angle between them. So, oh, and this is great. That's what's. That's what I want. And so now I can just plug and chug at this point. So n1 dot n2, first times first, plus second times second, plus third times third. That's going to be 2 minus 6, that's minus 4, is equal to the magnitude of the first vector is going to be square root of first component squared plus second component squared plus third component squared. The magnitude of n2 is going to be equal to first component squared plus second component squared plus, let's throw it in for completeness, third component squared, cosine of the angle between them. Now it's just solve for theta. Okay, well, let's do this. Oh, I'm going to get a negative answer here. Let's work it out. we'll see what this is. So that's going to be, if I simplify this, so cosine theta is going to be equal to minus 4 over root 182. So let's just solve this numerically. And now, so cosine theta is equal to minus, then we get our minus 0.29650. It's negative, so it's going to give an answer bigger than 90 degrees. It does. Theta is equal to 107 degrees. If we say that the angle between them though is 107 degrees, the planes are intersecting like this. It's giving us the big angle. We would want to express it as the small angle. So we're going to say 180 degrees minus 107. So our answer is going to be what? 73 degrees. And it might be nice if we work this whole thing out in radians instead. But we didn't, we used degrees. Now I'm talking about intersection of planes. That's our next question then. That's our next, how can two planes intersect? Well, two planes intersect on a line. What about three planes? Well, okay, two planes when they intersect always intersect on a line. What about three planes? Well, they could, three planes. One plane, two plane, three planes. They could, three planes intersect at a single point. That's one option. They could also intersect, well, they could intersect all on a line if I had one plane, two planes. So one plane, two planes, three planes, they all intersect on a line. That's a possibility. Or they could make a tube, one plane, two plane, three plane. They could make like a triangular tube so they don't intersect. You could even have two planes that are parallel and one that's not parallel, but there's no one intersection point. How can I tell if two planes are parallel? Oh, their normal vectors will be parallel. That's how. So you can look at the normal vectors now of a scalar plane, and you can see them, the A and the B and the C. So you could see if they have parallel normal vectors, then they must be parallel planes. If all three planes are not, if they're not all parallel to each other, then you could have this sort of triangular tube idea, or they could intersect like at the corner of a box. Okay, last question. Find the symmetric equation of a line. Okay, so that's that weird form, right? X minus x naught divided by d1 equals. But what do I need for an equation of a line? I need the direction vector, and I need a point on that line. Okay, find the symmetric equation of a line that forms from the intersection of these two planes. So I need a point on that line, and I need the direction vector. Now the point has to be, since it's the intersection, the point has to be on both planes. So give me any point that's on both planes. Well, if we were doing this algebraically, we would just like do an intersection. We would set this up with some kind of like elimination, or solve this equation for x, substitute it into here, or something like that. But we've got two equations, three unknowns. So I can pick an unknown. I'm going to pick, right now I'm just looking for a point on the line, a point that's on both planes. So I'm going to choose z equals 0. If I choose z equals 0, then I just need to find the xy that fits on both points when z is equal to 0. If I choose z equals 0, then to be on the first plane, x plus 2y has to equal 1. To be on the second plane, that has to be true. So now I've got two equations, two unknowns. So I can just solve for the x and for the y. Now I can use elimination or substitution, some kind of a method to solve these two equations, two unknowns. I'm going to multiply that top equation through by 2 so I can add those equations together. No, so I can subtract those equations. So 2x minus 2x is 0. 4x minus a minus, that's going to be 7y equals minus 7. So that tells me that y has to be minus 1. If y is equal to minus 1, then, put it back up here. If y is equal to minus 1, maybe here, that's going to be 3, then x has to be 6. 3, x has to be 3. Am I right? That's going to be 6 minus 4 is 2, yeah. So now there's a point that's on the line, the intersection line. The point is 3 minus 1, 0. Now, I wanted the equation of a line, so I need a point and a direction vector. To get the direction vector, there's two different ways I can get the direction vector. If these two planes are intersecting, then the direction vector of that line has got to be perpendicular to the normal vector of this one and the normal vector of this one. So I could, to get the direction vector of the line, the intersection line, I could cross product this normal vector with this normal vector. I could do that. Yeah, I could do that. Or if I redo this process and get another point that's on the line, then I've got 2 points on the line. I'll just get the vector that joins the 2 points, and that's a direction vector as well. Which way is easier? Let's do the cross product. So I'm going to cross product the vector 1, 2, 3. 2 minus 3, 0. And this will be the direction vector. So I should get 9, 6 minus 7. Yeah, and if I check, that's perpendicular to both of those normal vectors. So this is the 9, 6 minus 7 is the vector I need, the direction vector of the line. All right, we're done. So the line, that's an L, is equal to the point that it goes through as a vector plus k times that direction vector. There's the equation of the, oh wait, that's the equation of the line, but that's not in the, that's the vector version, right? They asked me for symmetric equation. So I won't get full marks for that. All the information's the same, but I got to write it in the correct way. So that's going to be, oh, and I also forgot this one. So it's going to be x minus the x value of the point divided by d1 is equal to y minus the y value of that point divided by d2, z minus 0, I'll put it in, divided by the minus 7. Now I've given the symmetric form. That'll be full marks for it. Planes.